Hello and welcome to Physics Teacher. In this video, I'm going to go over how we're going to find and describe images in both curved mirrors and lenses, which is part of the curriculum for grade 10 science here in Ontario. Let's get started. So we're going to start with curved mirrors. Now we have three finder rays. Now these rays are rays that we can predict because they'll do the same thing every time. They're quite simple to draw and remember, and they don't require any protractors to figure it out. Now to find the image, you only need two of the three, because all you need to do is figure out where the reflected rays intersect. But depending on the example, you might prefer to use one of the finder rays over another, so let's look at what all three are. Now, a lot of textbooks use arrows as the object, and then we use arrows to find the arrow image. I just find that confusing, so let's just replace our object with a little stick figure here. We're going to figure out where the top of the head is going to form an image. So the first finder ray is that any ray parallel to the principal axis, where this is our principal axis, will reflect through the focus, like so. Let me draw my little stick figure here. Our second finder ray is very similar to the first, but in opposite order. If we have a ray goes through the focus, then it will reflect back parallel to the principal axis. And let me just write my arrows. There we go. The arrows are important so that when we find the image, we know which rays are the reflected ones. And our last one's the easiest one. If it goes through the center of curvature, it just reflects back on itself. All right, so let's use these finder rays to actually find some images. So here we have a converging or concave mirror. And for each one, we are going to find the image and then describe it. So let me change my arrow here into a person again, our little stick figure. All right, so let's start with the first finder ray. We're going to go parallel to the principal axis and then reflect back through the focus, like so. Then we can go through the focus. This is our second finder ray, and reflect back parallel. Now you can already see where these two reflected rays intersect, right here. So here is our little stick figure. Make sure you have the feet always standing on the principal axis. Now you don't really need to use the third finder ray in this case because we've already found where they intersect. So what we're going to do is we're going to describe it. We're going to use the acronym SALT, which stands for size, attitude, location, and type. So the size, you have to look at your image. Say, well, is the image the same size as the object? Is it smaller than the object or larger than the object? In this case, the image definitely looks smaller. Okay, what about attitude? Attitude means, is it upright or is it inverted upside down? In this case, it is definitely the opposite orientation as the object, so we're going to write that it is inverted. Location. To describe location, we can use these points, the center of curvature and focus, to describe location. We don't need to be super exact, but just in reference to those points. So I'm going to say it's between C and F. For type, we have two choices. We have real and virtual. Real images form where the light rays converge. If the light rays do not converge, you do not get a real image. So this one, they converge right there. So this is going to be real. And we'll get to an example of a virtual image later on. All right, let's try the next one. So the next one, all we're doing is we're taking our object and we're placing it at different locations for this converging mirror. And these are all the possible different examples you could see on your test. So we're going to draw our little stick person. That's what I prefer. And we can do the first one just as before. parallel to the principal axis and through the focus. Make sure I remember the arrows, and then through the focus and parallel to the principal axis. So this intersects right here. So when you have, I drew the head a bit big, but when you have an object right at the center of curvature, you get the image right at the center of curvature. So let's do our description for salt. The size is going to be the same size. Attitude is still going to be inverted. The location will be right at C, and we still have a real image. All right, what if the object is between C and F? What do we get this time? So we'll go parallel and through F, and then through F and parallel. So here's our image right there. I always forget the arrows, but they're important because we want to see where the two reflected arrows intersect. Okay, sometimes students will say, oh, it intersects right here at F, but that's not true because this is not a reflected arrow. It's an incident arrow. These are the two reflected arrows. Those are the ones we care about where they intersect. So our image is right here. So if we describe this with salt, the size, definitely bigger. Attitude, still inverted. The location is going to be past or beyond C. All right, beyond C. And the type is still real. Okay. Now we're going to do some trickier examples, because we're going to bring the object even closer. So now the object's right at F. So our first find array, pretty easy to do. Just put in my little person here. First find array, parallel to the principal axis, and reflect through the focus. But in this case, the second find array is a little tricky. I can't just have it go through the focus, because then it's just going to go straight down. That's not going to hit anything. So we can use the third find array. Now we can't have it go directly through C because it's just going to keep going without hitting the mirror. So what we're going to do is we're going to have it come from C and hit the mirror. And then it's going to reflect right back upon itself, like so. Now in this case, these two lines are parallel. So they're never going to intersect. And if they never intersect anywhere and they're parallel, we don't get an image anywhere. No real image and no virtual image. So what is a virtual image then? Let's look at this example. Here we have our object inside of the focus. So I can start with my first ray, go parallel, and then through F. And then the second one we can do as if it's coming from C. And it reflects back on itself, like so. Now, these two rays are not going to intersect, but they're not parallel either. They're diverging. So if we had our eye right here, there's our eye, and these rays hit our eye, our brain would trace these rays backwards to where they do intersect. So they would be traced back to here. Now this is what we call a virtual image, because the light rays never actually intersect. Our brain just assumes they do and forms an image for us. So if we were to describe the image using salt, the type is going to be virtual, because it's not real. And the size definitely bigger. the attitude is going to be upright. This one is not inverted. And for the location, we're just going to say it's behind the mirror. All right, so these have been all different examples for converging or concave mirrors, but what about a diverging or convex mirror? We're going to use the same finder rays, but we're going to sort of tweak them a little bit. So here's our person. The first finder ray, we say it goes parallel to the principal axis and then refracts through F. This one we can't reflect through F. F is over here. But we can reflect as if it's coming from F, like this. And that's how we're going to draw it. Now the other one, we can do the second one as well. We can aim it at F, like so, and then have it reflect parallel. And you can do the same thing with C. You can aim it directly at C and then have it reflect right back upon itself. Well, I've got these two here. But again, if I had my eye here, okay, these rays are diverging, but our eye, our brain, is going to take these rays straight back to see when exactly they actually do converge. And they're going to converge right here. So we are getting another virtual image. So if we were to describe it, the size is going to be smaller. Attitude, upright. Location is behind the mirror. And our type is going to be virtual. Now, with a converging mirror, the description of the image will be different depending on where you place the object. But for a diverging mirror, I can place the object much, much closer and do the same thing, straight and reflect like so. I forgot my arrows on this one. And the other one can be aimed at F and reflected straight back. And then when we trace these rays backwards, again, we get an image that is smaller, upright, behind the mirror, and virtual. So changing the position of the object does not change the properties of the image. Okay, now let's look at lenses. So we're going to go over our three types of finder rays. They're very similar to mirrors, but there are slight differences. One of the differences, we don't have a center of curvature. We also have something called the optical center right here. Another difference is we're going to have two focal points. The reason why you have two focal points is because you can have light enter from both sides of the lens, right? Whereas a mirror will only reflect off the one side. So this is F, and this is going to be F prime. Now instead of C, we're going to have twice the distance, 2F and 2F prime. All right, so let's look at our finder rays. Our first one, we're going to go straight parallel to the principal axis. This is still called the principal axis. And we're going to go right to this center line that goes through the optical center there. And then it's going to refract through the focus. So instead of reflecting, it's going to refract. Still goes parallel to the principal axis and then through F, but we're refracting instead of reflecting. Now the second one, the second finder ray, does not go through F first. It's going to go through F prime, like so. And then it will refract parallel to the principal axis. So that's our second ray. And our third ray is going to go straight through the optical center without refracting at all. So those are our 3 find arrays for lenses that is going to help us find images. Let's do the same thing as before. Let's find some images. And this time we're going to move the object from beyond 2f to at 2f to in between 2f and f prime, and then we'll come to f prime and inside f prime. And then we'll look at some diverging lenses as well. So this lens is a converging lens, and it's also called a convex lens due to its shape. If you don't know why the names for lenses and mirrors are converging, convex, concave, and so on, you can check out my short video here that explains how those names work. All right, so let's start with this object. Let me draw my little stick figure. Okay, first parallel and through F. And the second one through F prime and then parallel. And we're looking to where those refracted rays intersect, which will be right here. And then we can describe using salt. Size definitely looks smaller. Attitude, that's upside down or inverted. Location, if this is 2f and that's f, we're just going to say it's between f and 2f. And the type, the light actually does refract and intersect right at that location, so this is real. All right, let's try right at 2f. You're going to notice lots of similarities between our converging lens and mirror. First, if we go parallel and through f, then we can go through f prime and parallel. And you'll notice we get it right at 2f. So, salt. The size, same size. Attitude, still inverted. Location is going to be right at 2f. And the type is still real. All right, now we're moving it to between f prime and 2f prime. I should have wrote my primes here. We typically write the secondary focuses on the same side as where you put the object. But that can switch if I were to put the object on the other side. Right? So here is our little stick figure. I can go straight and through F. Might run out of room on this one. And the other one's going to go through F prime, and then I can just fit that. All right, so our image is here. Don't forget the arrows. Tell that to myself. Okay, so S-A-L-T, size, bigger. Attitude, inverted. Location, if that's 2F, this is beyond 2F. And the rays actually go there, so this is real. All right. Hope everyone's okay with that. Let's try some harder examples now, because we are going to place the object right at F prime. So what's going to happen? We do have a similar case to the converging mirror. If we go straight and then through F, and then can't go through F prime, so we're going to use find array number 3 and go right through that optical center. And if I do that, these lines are parallel. Okay, they'll never meet. Even if I have my eye here and I see them, my brain will trace these back and they will still never meet because they are parallel. That's our definition for parallel. So no image. All right, let's try the second one. Here we can go draw our little stick figure straight and through F. And then I can go straight down through the optical center. Now, they're not going to meet, but they're not parallel either. So if I had my eye here, my brain would trace those rays back, looking for where they would meet. So they're going to meet here. Huge. Okay, so if we did salt, size, definitely bigger. And this is what a magnifying lens is. Attitude, upright. Location. For location, I'm just going to say the location of the image is on the same side of the lens as the object. So I'm just going to write same side as object. And the type, because those light rays don't actually intersect and we needed our brain to imagine them going backwards and intersecting, this is virtual. Okay. One more example. What about a diverging lens or a concave lens? All right, what are we going to get? Let's draw our object. So the three find array rules, here's how they're going to work. We can have one go straight, parallel to the parallel axis, but it's not going to go through F because that would be converging. So what it's going to do is it would diverge as if it's coming from F prime, like so. The second ray, you can have it go through. I don't really hit the lens there. So the second ray I'm just going to have go right through the optical center, and it will not refract. Okay, these two rays are obviously never going to intersect. But now as I draw my enormous eye, right, my brain will trace those rays backwards. So we'll have this one coming back and this one coming back. And you can see they intersect right here. So if we describe that, the size is going to be smaller. Attitude, upright. The location, I'm going to say same side as object. And the type will be virtual. And just like our diverging mirror, a diverging lens will give you the same properties for your for your image, regardless of where you place the object. So I hope this video has helped. And if you've got a grade 10 science test in optics coming up soon, good luck.